Today we're going to start into chapter 13 in the TRO textbook. The topic is solutions. So to begin with, we'll just talk about some terminology and then we'll get into calculations using concentrations of solutions by the end of this video. And then we'll start a separate video where we'll talk about types of solutes and some stoichiometry problems with solutions. So to begin with, what is a solution? The definition of a solution is a homogeneous mixture. Now, most people think about solutions as only being liquids, but you can certainly have solutions that are in different states of matter. As a matter of fact, if you mix gases together, they would always form a solution because they would be homogeneous because they're moving around randomly. But you could even have solid solutions, things such as brass or different metal alloys, where they make them by heating the metal to a point where it becomes liquid, and then they mix them together as liquids, get to mix homogeneously, and then they cool them, and as they cool, they become solid again, but they are now mixed in a homogeneous, spread out evenly throughout the entire sample. So solutions are not always liquids, although that is the most common. When you have a solution, there are two main parts, or two main categories of parts. There is a solvent, and there is solute. Now you could have only one solvent, but you could have one or more solutes. Solvent is the component of the mixture present in the largest or highest amount. And solute is the component present in a lesser quantity. There are a couple of exceptions to this. If water is involved, it's always taken to be the solvent, regardless of how much. So I know we haven't done concentrations yet, but this is just percents. If you have rubbing alcohol, that is 70% isopropyl alcohol. Well, if it's 70% isopropyl alcohol, it's only 30% water. Yet water would still be taken to be the solvent, and the isopropyl alcohol will be the solute. If I have a glass of water and I put sodium chloride into it, water would be the solvent. Once the sodium chloride's in there, it would be the solute. But I could also take that same glass and put some sugar into it, in which case water is still going to be the only solvent, but now my solute would be sodium chloride and sugar. So you can dissolve more than one thing into a solution. However, that solution will still only have one solvent. Now, some other terms that you might see about solutions or talking about solutes is solubility. We're actually going to explore this in the lab as well, but the definition of solubility is the maximum amount of solute that will dissolve into a given amount of solvent at a given temperature. So talking about what's the most solute I can get to dissolve into a certain amount of solvent. And there's a couple of different factors that affect this. The factors that affect solubility is obviously temperature, because it's right in the definition. Temperature has different effects on different solutes, but there's some general statements. In general, for solid solutes and for liquid solutes, if you increase the temperature, you will typically increase the solubility, meaning you could dissolve more. So if I had a cup of coffee and I put sugar into it, and it was very hot, I could dissolve a lot of sugar. But if I let that coffee get cold and I try to dissolve the same amount of sugar, I could get lots into the hot one. I could only get a little to dissolve into the cold. That's because the solubility is decreased with the temperature. That's not true for all things, but it is true for most solids and liquid solutes that if you increase the temperature, you will also increase the solubility. If you have gases, if you have a gaseous solute, the reverse is true. If you increase the temperature, typically the solubility goes down. This makes sense if you think about it because gases are moving around rapidly and randomly, and if you give them even more energy, they're going to be able to expand more and move right on out of the solution. So these are things that are important in marine biology because things living in water need to have dissolved oxygen to live, and warm water will have less dissolved oxygen, and therefore it can't support as much life as cold water, which can dissolve much more oxygen. So we'll come back and do a little bit more of that in a bit. So if you look at solubility versus temperature, you can get to what's called a solubility curve. It's deceiving sometimes to call it a curve. Sometimes the relationship is linear, but not always. So they just use this generic term of curve. And so what you do in a solubility curve is you look at how much will dissolve at different temperatures. And typically when they look at the solubility, they look at the number of grams of solute that will dissolve into 100 milliliters of solvent. Remember, the definition is how much solute will dissolve into a given amount of solvent, and the given amount in this case is usually set at 100 milliliters. And so what you can do is see how much will dissolve at different temperatures and you plot it. So just making up numbers, 5, 10, 15, 20. So at a lower temperature, you're only going to be able to get a maximum of, say, 5 grams in there. But if something's solubility curve looks like this, by the time you can get 15 in, you'd have to be at a much higher temperature. So maybe this is at 15 degrees Celsius, where maybe by the time you're here, you're up to 25 degrees Celsius. So as the increase in temperature, you'll increase in solubility. Now, if you look at this type of curve, you can actually talk about, use different terms for the solutions that would be created. If a solution contains the maximum amount of solute, that solution is said to be saturated. If the solution contains less than the maximum amount of solute, then that solution is referred to as unsaturated. It's not fully saturated with solvent. You could put more in. There's actually a third category, although it's not very stable. If the solution contains more than the maximum amount of solute, then that solution is actually called supersaturated. Now, supersaturated is really kind of unstable, and they're very hard to form, supersaturated solutions, but sometimes they do happen. If you dissolve solute in, and you have the solution being very high in temperature, so it's very warm, and you cool it ridiculously slowly, what can happen sometimes is, whereas most of the excess solid or liquid solute should start to come out of solution, occasionally it will stay in solution, and for that moment it would be considered a supersaturated solution. Those are very unstable, and as soon as you tap it or touch it, all the excess solute will precipitate out of the solution immediately. So if you're interested in seeing that, go to YouTube and look up supersaturated solutions, and you'll see sodium acetate is one of the most common substances that do it. So if you YouTubed supersaturated sodium acetate solutions, you'll probably be able to see that done live for you. So where on this graph would these things fall? So if this line is telling me how much can dissolve, if I'm underneath that line, if I have a solution that at 15 degrees only has 4 grams of solute in it, it's underneath, below the solubility curve, this solution would be unsaturated. Because at 15 degrees, the maximum is 5 grams, but we only dissolved, but only have 4 grams dissolved. So you contain less than the maximum unsaturated. Less than maximum is always considered unsaturated. If you happen to fall, let me see if I can get a different color. If you happen to fall directly on the curve, any of the points directly on the curve, that would be when you are saturated. All points, excuse me, all points on the curve represent a saturated solution. So where would you find supersaturated? You would find supersaturated if you were above the curve. Again, these are not very common, and they're certainly not stable. So you have saturated on the curve, unsaturated below the curve, and supersaturated above the curve. So when you're in a lab, we're going to actually collect data and build a solubility curve for potassium nitrate, so you can get an idea of that. Okay, so far the factors affecting solubility, let's not use that color. So far the factors affecting solubility that we talked about is temperature. The second factor is pressure, but this really only affects gaseous solutes. And what's true is if you increase the pressure, you will increase solubility. This is what they use to make carbonated drinks. What they do is they have a bottle of soda, and they'll pump CO2 into it under high pressure and then cap it. But as soon as you open the cap, what happens? It bubbles. That's because the excess CO2 gas escapes. And if you open and close that bottle of soda, the excess carbon dioxide will keep coming out until there is no more excess carbon dioxide. And at that point, you would say the soda is flat, or it just won't bubble anymore because it's no longer got extra pressure pushing that carbon dioxide in there. You've released all that excess pressure. So pressure will only work on gaseous solutes. It really has no effect on solid and liquid solutes. The third thing, I'm just going to kind of call it nature of the solute. A lot of this material is actually skipped over in chapter 12 of the Tro book, and when you take Chem 1A, you'll see a lot more of it. But there's this general rule that says like dissolves like, and what this means is that polar solutes will dissolve into polar solvents, and vice versa. Nonpolar solutes will dissolve into nonpolar solvents. So as a quick example of something that you know is if you try to mix oil and water, you know that if you put oil and water together, regardless of how hard you shake it, once you stop shaking it and you let it sit, the oil and water separate out again. So you're going to end up having two layers. You'll have oil on top and water on the bottom. The reason that oil and water don't mix is because oil is nonpolar and water is polar. So they're not going to mix into each other. So in the textbook, and I attached a copy of it. Actually, I think I put the information on the homework assignment. There's a list of some common polar solvents, and there's a list of some common nonpolar solvents, and there's a problem or so at the end of the chapter that asks you to predict whether things will mix or dissolve. And all you need to know is that nonpolar things will go into nonpolar solvents, and polar things will go into polar solvents. As you move into Chem 1A, you'll go through a lot of what's going to be called you're going to look at the properties of molecules and solutes that allow this to happen, and you're going to study what are called intermolecular forces. And that's really, if you wanted to read up on it, it's in chapter 12 of the TRO text. But we're not going to cover that in this class. But the reason that like dissolves like holds is because of these intermolecular forces. They're important in biological systems, and they're important in all solutions. So you'll learn more about that in Chem 1A. The last thing I wanted to talk about in this video is once we start talking about solubility and how much solute is in there, what we're really talking about is concentrations of solutions. Concentrations of solutions is a way to try to tell you how much solute is in how much solvent. Now the problem with concentrations of solutions is there's probably, I don't know, at least 10 different or more units of concentration of solution that are out there. We are not going to cover them all in this class. As a matter of fact, we're going to cover two main ones, and that's it. The textbook only covers two. I'm going to expand one of them a little bit for you. But the two that we're going to look at are percents and molarity. And I'm going to talk about each one of those separately. But I just also wanted to mention that there's two general terms that you might see. You might see a solution called concentrated, or you might see a solution called dilute. If a solution is concentrated, it's not telling you exactly how much, it's just stating that there is a high quantity of solute present. It doesn't tell you exactly how much, but it's telling you there's a lot of it in there. And dilute is stating that there is a low quantity of solute present. So a concentrated solution contains more solute per amount of solution than a dilute solution would. So if you have a solution, and let's just use a percent for right now, and it's 20% sodium chloride, and then I take that solution and I add water to it, you might hear the word you're diluting it. So now my sodium chloride, however much I had in here, say I had 5 total grams, total of 5 grams of sodium chloride in here, I'm still going to have a total of 5 grams of sodium chloride, but now it's going to be more diffuse in there because I've had more solvent in it. So this one would be more concentrated. This one would be less concentrated. Or you could say that this one is more dilute and this one is less dilute. Those are just some generic words, concentrated and dilute, that you might see. So let's get to the actual math of them. If you look at percents, percents are always part over whole times 100. That's just a generic version of what a percent means. So for us in solutions, in your textbook, they only show you one. They show you percent. It's called mass to mass. And what the units here are, the part is going to be the solute, and the whole is going to be the solution. And so the different percents are based on how do you measure the amount of solute and how do you measure the amount of solution. So in mass to mass, you're measuring the mass of solute and the mass of solution. So this is going to be the number of grams of solute divided by the number of grams of solution times 100. Now, solute is just one component of the solution, and solution is the solvent and solute, right? So this is solute plus solvent. So it's the whole thing. But this is the only one that your particular textbook talks about right now. But there's other common percent ones that you'll see also. There's percent mass to volume, in which case you take the number of grams of solute and you divide it by the number of milliliters of solution times 100. So this one is very common to see, although your textbook doesn't do it. And the third one I wanted to talk about is percent volume to volume. This is the number of milliliters of solute divided by the number of milliliters of solution times 100%. So all three of these formulas are common to see. The grams of solution works out really well because masses add well. If I have 5 grams of solute and 20 grams of solvent, then my solution has a mass of 25 grams, right? I could just add them together. So masses are additive. You could just add them. The problem with the other two here is that volume is in there, and the volumes are not additive. Sometimes they are, but they're not guaranteed to be additive. So you can't say if I take 5 milliliters of solute and 20 milliliters of solvent, you can't say that that's going to give me 25 milliliters of solution. That's because sometimes they fill in the holes of each other in the densities. And so that the density of the solution of the solute and the density of the solvent are different, then the density of the solution is going to vary as well. So volumes, you can't just add them, whereas masses, you can always add them. So these two are more difficult to deal with because of that problem. And that's, I believe, why your textbook probably just skips over them. So those are 3 formulas that I'm going to ask you to know. And then there's one other, and then we'll jump into doing problems. The other type of concentration that is very common and used the most in chemistry is molarity. Molarity is abbreviated with a capital M. And molarity stands for the number of moles of solute. And now you have to watch out for this one, divided by the number of liters of solution. When they do percents, they use milliliters of solution. When we're talking about molarity, you must be in liters of solution. That's an important distinction in the problems, and I know it confuses some people. So let me show you some problems, sample problems, and see how you're going to use these equations. Here's our first sample problem. If 15.0 grams of hydrogen peroxide are dissolved with water, and the final solution volume is 50 milliliters, what is the percent volume to volume? That's a W, sorry, concentration. And so if we're talking about volume to volume, then I want to use my number of milliliters of solute divided by my number of milliliters of solution times 100. So in this problem, this is my solute, and this is my solution. And so then it just becomes a kind of a plug and chug problem where I'm going to say I have 15.0 grams of solute divided by 50 milliliters of solution times 100, and keeping with sig figs, that would give me a 30% volume to volume solution. So they really are that easy, that simple to do. So here would be another problem. What is the percent mass to volume concentration if 15.0 grams of sodium chloride is dissolved into 75 milliliters of solution? In this case, we see we have mass to volume, so our formula is going to be number of grams of solute, mass, divided by volume of solution, number of milliliters of solution, times 100. My number of grams of solute, 15. My number of milliliters of solution, 75. All I have to do is plug and chug. 15.0 grams of solute divided by 75 milliliters of solution times 100. 15 divided by 75, I think is 20%. And it should be 20% mass to volume, right? So there are no real units put into these, but they're usually indicated by the parentheses telling you. So if you see volume to volume, it's going to be, oh, I did that. No, I don't have you present to catch me. This should not be grams, right? That should be milliliters in that first problem. Milliliters to milliliters, volume to volume, whereas this one is grams to milliliters. And then the third type, and these two are not common in your textbook at all. The third type of problem would be if 15.0 grams of sodium chloride is dissolved into 85 grams of water. What is the percent mass to mass concentration? Now, what's tricky about this one that a lot of people want to do is this is my solute. This is not my solution. This is my solvent. So the trick that you have to know here is the formula we're going to use is percent mass to mass is going to be equal to the number of grams of solute divided by the number of grams of solution times 100. It's always part over whole, and the whole is always the whole solution. So this is not representing the solution, that is just a solvent. So to get your mass of solution, you need to add the mass of solute plus the mass of solvent. And so in this case, my solution is going to be 15.0 grams of solute. That's my sodium chloride. And I'm going to have 15.0 grams plus 85.0 grams. This is solute. This is solvent. And I'm going to have 100 grams of solution. So one of the most common things that people forget to do is add this, and they just plug in erroneously 85 here times 100, and I'm going to get 15% mass to mass. So those are the typical types of problems that just plugging in and finding concentration. In the homework, I asked you to do a few others where you're asked to find how much solute, and I'll show you one of those now. So here's another type of problem that you could be asked to do. How many grams of sodium chloride are present in 55.6 milliliters of a 35% mass to volume solution? So in this case, you're still going to use the formula. You see, it's mass to volume. So mass to volume is always going to be number of grams of solute divided by number of milliliters of solution times 100, right? That's our working formula. In the previous problems, you were given grams of solute and you were given milliliters of solution, and you were finding the concentration. In this case, this is given, and the milliliters of solution is given, and what you're asked to find is how many grams of solute. And so it's just algebra to do this, and you can set it up as dimensional analysis, you can plug and chug it as an algebraic problem, or you could even just set it up as a proportion. So if I know percent, 35.0% means I have 35.0 grams of solute per 100 milliliters of solution, right? That's what it really means, 35 per 100. Then I can use this as my equivalent statement. And I could do dimensional analysis to solve this, and I could say if I started with 55.6 milliliters of solution, I'm going to have 35 grams of solute per 100 milliliters of solution, and I could get my number of grams of solute. I don't have my calculator with me. I'm sorry, I won't be able to give you the number for that, but I'm sure you could figure that out. There's another way that you could do that a little more straightforward if you don't like that, is with the percents, you can set them up as ratios. So you could also say 35.0 grams of solute per 100 milliliters of solution is equal to X grams of solute over 55.6 milliliters of solution. And if you solve that for X, you do exactly the same calculation that we did over here. So either way you go, you can do that. And the homework problems are asking you to do a few of those. I wanted to show you one other problem before we end. And the last problem we're going to do has 3 parts to it. And so if you have 25 grams of potassium chloride dissolved in enough water to make 250. To make 250 milliliters of a solution that has a density 1.4 grams per milliliters. Calculate the percent mass to mass, the percent mass to volume, and the molarity of the solution. So there's 3 different parts to this. The hardest one of this is actually the first one, the mass to mass. So what do you need to do in order to do this? To find percent mass to mass, you need the number of grams of solute divided by the number of grams of solution. Now, the number of grams of solution is not given to you. What was given to us directly is the grams of solute and the volume of solution. So how do I get from volume to mass for my solution? What I need to do is use the density. So I'm going to use density to convert from volume to mass. Remember that density is equal to mass divided by volume. So it's a relationship between mass and volume. So I could say that my 250 milliliters of solution, I'm going to use my density as a conversion factor. My density is given right here in the problem, tells me that I have 1.14 grams of solution for every 1 milliliter. And I could calculate that out. And if I did that, what I'd have is 285 grams of solution. Now I know this and I know this, so I could just simply plug it in there. So my answer would be 25.0 grams of solute divided by 285 grams of solution times 100. And I believe if you calculate that out to 3 sig figs, you get 8.77% mass to mass. So that one's a little tricky. If the density was not given to you, you really wouldn't have been able to solve that. So how do we solve the second one? To solve the second part of that, we're going to need percent mass to volume. This is going to be my number of grams of solute divided by my number of milliliters of solution times 100. Now this one's much easier because those things are given to us directly, right? So what's given to me is 25.0 grams of solute, and what's given to me is 250 milliliters of solution. And so if I calculate that out times 100, I believe you get 10, 3 sig figs, 10%. This would be mass to volume. And my last one that we had to calculate is molarity. And to calculate molarity, we need the number of moles of solute divided by the number of liters of solution. So in order, and there's not times 100, you leave it as just the ratio. So for this one, there's two things that I need to convert. I have to take my 25 grams of potassium chloride and convert that to moles of potassium chloride. And I have to take my number of milliliters of solution and convert that to liters of solution. And so to get that done, you need the molar mass, 25 grams of KCl. If you add up the molar mass for KCl, potassium is, chlorine is 35, and potassium is, I believe, 19, there's 20. I look them up. I only wrote down my total. I didn't write down the individual ones. I know that 1 mole of KCl is 74.5 grams of KCl. If I calculate that out, I'm going to get 0.335 moles of KCl. I need that for right here. Here's my moles of KCl. Now I need to take 250 milliliters of solution and convert that to liters. And I know that 1 liter is 1,000 milliliters. And so this is going to be equal to 0.250 liters of solution. I need that for the bottom. So now I'm ready to calculate it out. So I have 0.335 moles of solute divided by 0.250 liters of solution. And if you calculate that out, I believe you're going to get 1.34 moles per liter, or you could write that as 1.34 capital M. So I'm going to stop here. We're going to do a little bit more with molarity as we're coming up, and we'll do a couple more calculations in the second video. I hope that goes okay for you, and that now you should be able to do the majority of the homework problems assigned to the chapter as well.